Welcome back to exponential and logarithmic equations. Today we're going to look at particular types of logarithmic equations. So a log equation is one where the variable is in the log, like it's the argument of the log function. And maybe we need a way to get it out. What we're going to be using here will be some of the laws of logarithms so that we can express things in the form where it's just one log is equal to another log, and those two logs have the same base. Because if that's the case, if two logs are equal and they have the same base, then we can say that their arguments are equal. So the things that we're taking the log of, we can say those are equal. But only in this case, where it's just straight up log equals log, and they have the same base. If there's anything else there, if this is like a 2 instead, then we don't have log equals log. Or if we have plus 1 or something, like that, then it's not just straight up log equals log. And we need that. Now as we go through, there will be one word problem at the end, which should have been in the other section, unfortunately. I'm sorry I didn't put it in that proper one. But we'll go through these three examples, which are very specifically about solving logarithmic equations, and then we'll do a word problem that ties into the previous topic with evaluating logs and solving contextual problems. So we're going to solve these. In this first case, we already have the situation that log equals log. Like it's already there, hooray. And we can say that 3x plus 4 is equal to 19, that the arguments of the logs must be equal. Of course, we will have to note that there is a restriction because we can't take the log of anything that's not positive. So if it's 0 or if it's negative, that's bad. So at some point, just make sure you state that because the variable's in the log function, that we have a restriction. In this case, x has to be at least, no, not even at least, it has to be more than negative 4/3. If it is 4/3, then this whole thing will be 0. Can't have that. So do state that restriction. But once we've established this, from log equals log to some statement about their arguments, we can just straight up solve. And we can then say that, well, 3x must be 15, x must be 5, and this thing is done. I dare you to try the others. See what happens. And let's go for it. Remember that you will need to make sure it says log equals log. If you don't have that, then you cannot proceed. What did I do? Did I undo things? Oop. Sure. Don't mind me. Alright. Hopefully you've paused and tried these already. I'm going to now start. So we don't have log equals log here because of this 2 in front. I need a way to incorporate it in this log here. And for that I will use the power law of logarithms to say that this is the same thing as taking log base 2 of x plus 1 squared. The right side is exactly as it is. There's nothing we can do with it, nothing we need to do with it either. And at this point we have log of something equals log of something. And those logs are both with base 2. So we can say, as a result, that their arguments must be the same. That x plus 1 squared must be equal to x plus 13. And now we're just solving this quadratic equation instead, which isn't so bad. So I'll open up those brackets. I'll punch everything to one side. And I'll factor and solve. Two possible answers. Wow. Careful though, because we still need to check these against our restrictions. Because we're taking, again, log of a variable expression, we have the potential for restrictions. This one here says that x must be greater than negative 1. This one also exists, and it says that x has to be greater than negative 13. But as long as it's greater than negative 1, this one will be covered. So really the only one that matters is that. You can still state both if you want, but the minimum to state would be this one. Because x has to be at least, or over -1, this answer is not valid. It is technically extraneous. It happened when we essentially took 2 to the power of each of these sides. So as a result, we're going to say that that answer isn't valid. And for good measure, we'll put a box around this one to say this one is. Last of these 3 is this one. Again, we don't just straight up have log equals log. We've got this 1 kicking around here. And it's not even in a log at all. So we're going to have to do a couple things. One is to actually say that 1 is the log of something. And then we'll have to take that log with this one and combine them into 1. Again, give it a try. Give it a go. Give it a whirl. Maybe I'll state some restrictions. X has to be at least -4/8. And this one says x has to be at least -1. All right. So left side, I'll leave as is. Right side, I need to write this 1 as a log. Log 10 is equal to 1. So that's that change there. And then this other log, I'll leave same. So that's all that happened here. I turned that 1 into log 10. The reason I did that is now I can take these 2 logs and write them as 1. And for that, I'm going to use the product law of logs. So this left side stays exactly the same. On the right side, using the product law of logarithms, I can say is the log of 10 times x plus 1. And that's again from that law that just says log of mn is log m plus log n. Right? So that's easier m and n right there, and there's the product mn for that formulaic perspective. Now we have a statement of log equals log, and we can say that their arguments are equal. That 8x plus 4 must be equal to 10 times x plus 1. And solve this however you will. There are a few ways to proceed, I guess. I personally prefer to just open up these brackets and go from there. Subtract 10 from both sides, subtract 8x. And there's that. Don't forget to check against your restrictions. X has to be greater than -1/2, and it has to be greater than -1, which -3 is not. It was our only answer, and we rejected it. Therefore, there's no solution. It's so sad. So that's the basis of solving logarithmic equations. Again, there's a word problem on the next page, a contextual scenario. Kind of relates more to the previous section, but it's good practice for us nonetheless, so let's tackle it. Radioactive decay. Ooh. So it happens in unstable isotopes. Here comes the chemistry part again. Atoms lose energy by releasing radiation. And the rate of decay is different from isotope to isotope. So plutonium-239 has a half-life of 24,000 years. So if you've got like some mass of plutonium-239, after 24,000 years, you're only going to have half of that. And then after another 24,000 years, you have half of that amount. So it's not like the 100% is gone after 48,000 years. It keeps reducing by 50% after that much time, relative to what it was like 24,000 years prior. So if you had, here's the example. If you had 2 pounds of it now, then you'd have, whoa, who's putting typos in here? Sorry, everyone. There should be 24,000 years there. and this should be 48,000 years there. So that's worth noting. Now, the mass remaining of a particular element or isotope can be given by this formula, where A sub naught is the initial amount, A is the amount you have now, time is in years, and this is the half-life, which is also in years. And there's another way to write it, which is that, as just kind of using exponent laws to play around with that base. So August of 45, August 8th, I think, an A-bomb had 14 pounds of plutonium-239 that was dropped on Nagasaki, which, well, was a doozy in that war. So not all of it remained. 2 pounds underwent nuclear fission, caused a catastrophic detonation. And we're going to take some liberties with this question here. We're going to assume that the remaining 12 pounds just scattered over the blast area. And we're going to assume that no cleanup efforts were done. We're just going to say, yep, that's what it is. And we're going to see how much of it remains today. And when we say today, for the purpose of this question, we're not going to necessarily say January something of whatever year. We can, for this we can assume it's close to 75 years ish. If we want to get closer, based on it being August 8th of 45 and January being 5 months after that, it's closer to like 75.417. But for this example, we can use straight up 75. So listing what we've got, A sub naught, the initial amount was 12 pounds. The half-life is 24,000 years. The time is 75 years, because it's been 75 years since. And we'll now plug this into the formula. How much of it remains today? I'll use that version of the formula. You can use either one. Plug in what we know to the power of negative 75 over 24,000. And we get a value out of that of 11.974, which is not a whole lot less. It's a lot. But the other part of the question is, when will only 9 pounds remain? And for that, we're going to use that same formula. Oops. 2 to the power of negative t over h. And we'll fill in what we know in that case. A in this case is 9. Right? Our final value is 9 pounds. The initial value is still 12 for 12 pounds. Now, we don't know the time in this case, but the half-life is still the same. And we're going to work to isolate t. So dividing both sides by 12 gets me here. And now I've got a power on this right side. I should take the log of both sides, because that's the only way I'm getting that exponent down. This particular step I'm writing, you don't have to write. You can jump straight to the next one. That is acceptable. But I figured I'd just write it in for now so we can see where particular things came from. So using the power law, this exponent got plunked down in front. And that's because we applied the log. So proceeding with this, to isolate t, I need to take log of 3/4. I need to divide it by log 2 because it's being multiplied by t. We're also dividing t by, say, negative 24,000. So I'll multiply by that. And now we can say t is isolated, which gets us a value using our calculators at this point, again being very careful with brackets and all that. To 3 decimal places, I'm getting that value. That's quite a lot of years. To be honest, I don't know if cleanup efforts, like 9 pounds, can be a lot. In some circumstances, you can say it's also a little. And it is over a very large area, so maybe, I honestly don't know. It's not something I've really looked into, and maybe it's worth looking into. But it's there for a while. So anyways, that's that. There is some practice work that relates to all this, that relates to both logarithmic equations and maybe some extra little word problems in there as well. I encourage you to give it a try, give it a go, give it a stab, give it a shot, give it a whirl, give it a spin, and see where that takes you. And as always, please ask questions as they come up. Questions on this lesson that you had as you're watching it, or maybe you're still watching, I don't know. Just make sure you let me know. And questions on the practice work as well. So that's that. I will see you in the future. Goodbye.